Here we go. So I put everything on recording. I'm going to go to share screen. Here we go.
Say good evening to the people just arriving.
Good evening. Hello, hello. So here we go. This is what I'm just going to do a quick review of what we covered last time. Nothing earth-shaking here, but we're starting our class off by trying to have a set of foundations, a common vocabulary. What is it that we could agree on, that we could have a discussion. And since the title of the class is Mysticism, where science, art, and spirituality meet, we're going to just walk through these progressively. So yeah, the first class we covered mysticism. This class we'll spend a lot of time on science, and it'll spill over into the next class of art and spirituality. So that's what we're doing. And what we did along the way here was we had a little overview of science, which you'll see in a second. But we have an issue that science is at a crossroads here, that after 500 years of active evolution of science, they've realized about 100 years ago that they were studying 5% of the universe, and the other 95% is called dark. And so this is a major issue.
Yeah.
They're going crazy trying to figure it out. We'll talk about what we think is a promising approach here. It's not blessed by them, but there's a lot of evidence that it is the basis for it. And then the other side of things, the problem we deal with here is that people claim that they're spiritual, but they're no longer affiliated with any organized religious group in the United States. And this is a growing group. This is the largest single group when you poll people in the United States. So the issue here is in part the organized religions are not meeting the needs of these people, and the spirituality is probably not integrated into most people's lives in any sort of meaningful way. Then we'll talk about mysticism, science, mathematics is going to play a role here, and art and spirituality. So that's what we started with last time. Here was our brief review of science, of what was going on here. And the thing to keep in mind, we stressed here, is things have been kind of on hold since middle 1970s in physics, where they've come up with a model. The model encompassed what they knew of mass and energy, but it ignored this 95% of dark that was out there. And the other piece to it was it didn't really include anything about gravity or the issue of space itself. So these are areas that show that this model is very incomplete. They've been working on it for 50 years and they haven't really come up with anything. But right now, there's a huge amount of activity with people trying new theories, thinking outside the box in very different ways. And perhaps in the next 5 or 10 years, there'll be a revolution that will occur, and we'll suggest what the framework of that is. So the key thing to keep in mind here was we had the notion of the geometry of the universe, with space having 3 orthogonal dimensions to it, and then time is totally separate, and gravity is just something that attracts pieces of matter to one another. This was modified by Einstein to show that space and time together form a 4-dimensional universe. So as you travel faster and faster, time slows down. So as you move through space, there's a coupling between space and time somehow that we have to sort out. And this led to Einstein coming up with this picture here of what he called general relativity, where matter itself curves space. So here we have a sun with a planet running around it, and the mass of the sun curves what we think of as space here, this is just a graphic to try and suggest what's going on, because the curvature would be in 3 dimensions, and this is just 2 dimensions. And then the planet runs around here, and the planet itself is curving, is generating curvature. So it was a very different view, but the thing that it showed was that as gravity increases, time slowed down. You know, you end up with hints that there's more things going on than we realize. And then in the 1960s, there was actually astronomical evidence that each of the galaxies in our universe has what's called a black hole, something that's the gravity is so strong, light cannot escape from it, so it's called black. If light can't get away, then when you look at it, all you see is black because there's no light coming at you. And every galaxy that we found so far apparently has a massive black hole in its center. The Milky Way galaxy black hole has a mass of 4 trillion masses of our sun, which is a mind-boggling number. There was one galaxy that was discovered with 100 trillion masses of our sun for its black hole at the center. So there's something going on here that we really don't understand. So Ron Cowan went through deep meditation, and this is following the Yoga Sutras of Patanjali, and he was able to see down into the microcosm and out into the far reaches of space. And beyond that, he was able to, for example, when he went down and looked into the microcosm, he could stop an electron. An electron would normally be flying at really high speeds around the nucleus of an atom. And he was able, through his capabilities in deep meditation, to stop it. And he could actually, as we'll see, draw a picture of an electron. There are no pictures of electrons. If you look in any physics books, that by itself is a great accomplishment. And then the other thing that he did was he went back and looked at the start of our universe, which many people called a Big Bang. And I pushed him on this repeatedly, and he said, no, there was no bang there. It was a big bounce. And there was no nuclear fireball that created all this stuff. It was just a bounce that occurred. But in doing this, what he mentioned was there appear to be many other universes out there, and then there's a void in between the universes. Well, this was something that theoreticians in physics came up with in the late 1970s. And it just raises the question of, well, if you have a universe with space and time in it, then what in the world do you call the thing that's between the universes? I mean, that's a different sort of space. So that's all I would say. But the other thing that Ron observed was that space itself is quantized. It's made up of little packets of space, and the packets of space, the walls of these space compartments contain blocks of information, and they're constantly scanning everything around them. And when they detect a change, then they consult the algorithms in these information blocks, and they end up changing things to follow these algorithms. So what he's observing here is that there's actually a control of the universe by these algorithms, which is, you know, if you read any book on physics and you talk about electromagnetism, you won't find anywhere that there's a control of electromagnetism. And yet it's all done through these algorithms here in these information blocks that Ron observed. So then we ran through some quotations of Einstein, which I'm not going to touch on. There's a bunch of quotes here. He was very much a spiritualist, and he believed in the God of Spinoza. And you know, his takeaway here was he was always being asked, "Do you believe in God? What is going on here?" And this is his philosophy, that he believes in the God of Spinoza. So then we touched on mysticism, and there really isn't any good definition of mysticism. It appears that the Greeks were the ones that first started it, with a Greek word meaning to close or to conceal. So mysticism is something that's concealed or hidden. It's mystical in that sense. But in our age and going forward in time, it appears to include a really broad range of beliefs and ideologies related to extraordinary experiences and states of mind. So that's what we'll use for mysticism here. That's our first component of the class. And the other thing that comes with this is that the aim here is to have a union with the absolute or the infinite or the collective unconsciousness, as Jung called it, or God. And this has been applied to a variety of religious traditions and practices, and so it goes. A lot of people have dismissed these mystical experiences, but there's a lot of people coming back to us saying, no, you missed something and you have to really look at this. So the one thing that has come through from all of these different mystics is that the world that we see with our eyes, the little person that's behind our eyes looking out, that's our consciousness, that world is an illusion. And that comes up again and again in all of these ancient and then much more modern texts that we see here. And Ron confirmed that. That's what we'll see here. But the mystic side to it is apparently that our physical body is linked to an immortal soul, and the soul links to the physical body at birth somehow. And then the soul has already agreed before it links up to have a set of goals to achieve in this incarnation. But once it incarnates, there's a veil of forgetfulness so that the soul can't remember what those goals are. And then at death, having free will, the person with its soul goes through life, and then the soul unlinks from the physical body and goes on to have its life assessed. And in doing so, it'll then look at what the goals were and did it achieve those goals? And so it goes. So some people argue that really our purpose here in life is to learn to love yourself and your neighbor. This is the teachings of Yeshua, or Jesus the Nazarene, to show compassion for others and to work through the karma of these past lives to grow and to learn. And as you grow, the sense of love grows with you. So we'll see. So here we are. This is our class for today, the 9th. Let's see what's going on. We're going to take a jump here into science. And a lot of this is going to be based partly on my personal run-ins with science over the years, as you'll see. So broadly,
introduce yourself a little bit.
Well, what you'll see in here is that when I was in graduate school and working on my doctoral dissertation, the person on my doctoral thesis committee, Roger Brockett, who was at MIT and then he moved to Harvard, he said, well, could you take a look at this work that was done on what's called exterior calculus? And so I looked at it and it became clear to me that this was exactly the equations of electromagnetism that were coming out of this exterior calculus. But the problem that I had with it was that, as you'll see here, it simply is a mathematical exercise to generate these equations. And there's no physics involved, okay? It happens that the equations match what goes on in the real world, as you'll see, but it's like a total disconnect. There's the mathematics is totally separate from the actual physical phenomena that were observed. And we'll get to all this later on. And then I published all this in a Journal of Mathematical Physics in 1974, but I did all the work in 1970. And then when we got to 2005, I got approached by someone who was a very, very capable person. And we had some interactions, and he pointed out to me that if you looked at a book by Arnold Sommerfeld, who's one of the great physicists in Germany in the 1920s. He had as students 4 different Nobel laureates, and he himself was no slouch. But Sommerfeld had published a series of books trying to summarize his understanding of physics, all aspects of physics. So electromagnetism, optics, mechanics, partial differential equations as they relate to physics, and so on, and statistical mechanics, of course. So in doing this, he published in one of his books, here's Maxwell's equations, and that's on the left-hand page. And now we turn to the right-hand page, and here are the equations for fluid mechanics. Fluid mechanics means we'd have a fluid like water or something else. And the equations in form are identical, except that the equations for fluid mechanics encompass extra terms that relate to the density of the fluid. There is no fluid that was hypothesized in Maxwell's equations. However, there was a big push in physics after Maxwell came up with these equations, and the big push was to include a fluid which they called the ether, which allowed waves to propagate through space, because Maxwell's equations allowed propagation of electromagnetic energy, waves that would go through space. And if that's the case, there should be some fluid. Now, the fluid that's there, the ether, is in fact the quantum compartments of space, the little space compartments that make up a foam, is what we call space. And these compartments allow particles to hop from compartment to compartment to compartment. That's how they move. But the movement is very discrete. You're in one compartment, and you hop to the next one instantaneously, and so forth. So if you include these extra terms in Maxwell's equations, you end up with with more equations. And then if you carry out some analysis, a lot of things happen to occur there. And we'll get to that. So that's where we're heading. So now we're going to focus on electromagnetism simply because it appears to be the basic force in the universe that acts on everything, both matter and dark matter, as we'll see. And it will also allow us to account for dark energy. So that will be that, and that takes us into the issue of what is time. And we're going to come up with a very different view of time from what has been done in the past. So we're going to have space, and we're going to have time, and they're going to be very different. Then there's a much more modern approach to what I just call the classical approach, which relies on what are called emergent theories. So in these emergent theories, order arises or emerges out of chaos. And there's a lot of interesting examples for this. For example, tornadoes are an example of order that arises out of chaos. There's an incredible storm going on, and all of a sudden this order occurs, which is the funnel of the tornado. Or the hurricane that we're just talking about at the start of the class. A different example in physics is superconductivity, where all materials apparently have this property. If you cool them to a sufficiently low temperature, then they conduct with no resistivity, and some of them have no magnetic field inside them as well. So this is a very interesting property, and would allow you to, for example, have electric power transmission over huge distances that would be economical, that we couldn't do today because of the losses that we incur in transmitting electricity. So there's going to be two different approaches here. Really, this class, we're going to really focus on this classical approach, which is what was based on Ron Cowan's observations. And then in the next class, we're going to focus on this notion of what we call emergent theories, theories that arise out of nothing, out of chaos. So let's begin. And I thought the right place to begin is we go look in the Bible, because this is an old book. And in the Gospel of John, this is the beginning of the Gospel of John. And so what does it say? It says, in the beginning was the Word, and the Word is with God, the Word was God, and the same was in the beginning with God. So all things were made by him, and without him was not anything made that was made. And so what this is saying here is there's some entity, which apparently is called the Word, and the Word is with God, and that this entity made a decision. And the decision was, I'm going to create a universe, and in the universe, I'm going to populate it with life. And I'm going to watch how these things evolve. And I'm going to learn from this things that I couldn't possibly learn by not having this as a school in front of me. That's one interpretation. So what we have here is, in him was the life, and the life was the light of men, and the light shineth in the darkness, and the darkness comprehended it not. So we have this darkness, and this entity, God or the Word, created the light in this darkness. And that was started the creation of all of these different universes that are out there. And so it goes. So this is the start, one start of it, that suggests that there was a void, and then this entity created things in it. Let's look at the other one. This is out of Genesis. In Genesis, we find in the beginning, God created the heavens and earth. And now the earth was formless and empty, and darkness was over the surface of the deep, and the Spirit of God hovered over the waters. So there'd already been waters created, and God said, let there be light, and there was light. So he populated stars everywhere, and God saw that the light was good and separated the light from the darkness. And he called the light day, and the darkness he called night. And there was an evening and there was a morning of the first day. And so you can see that what's going on here is again a metaphor, and perhaps multiple universes were created. And to make things interesting, our universe is governed by a set of algorithms, evidently, with a particular set of parameters. And people call this meta-mathematics. It's above mathematics. The algorithms and that actually do all this control are above meta-mathematics. The universes that are there each have these algorithms, but they could have different parameters, and they could evolve very differently. And so whoever did this creation could be learning a lot from all of the many, many universes that are out there. So we'll see. This is just two different spins on something that was there in an ancient text, and we'll see what happens. Now, when you go through modern physics, there's a discussion of forces in the universe. And the statement is that there's 4 forces in the universe. There's gravity, which attracts matter to one another. There's electromagnetism, so we have things that have positive charge, things that have negative charge, and they generate fields that radiate out from them. The positive and negatives attract. The likes, the positives and the positives and the negatives repel. And so that's electromagnetism. Then we have the strong force. When we go into the atom in its nucleus has protons, and each element there if we look at all the 92 naturally occurring elements, they get more and more of these protons there, but the protons are all positively charged. And so somehow there's a flip in electromagnetism, but a strong force takes over, and at very short distances, positive will attract positive, so the nucleus will stay together. But there's also a weak force. The nucleus of the atoms have neutrons, and the neutrons will decay, and they'll generate a proton, an electron, and a neutrino, and the electron will get run off. But the proton that's there will create an isotope of whatever the atom was. So we end up with these four forces: gravity, electromagnetism, strong force, and weak force. And in fact, the correct statement is there's only one force, which is when we include the ether in electromagnetism, which we call etheric electromagnetism, then we end up with just one force, which is etheric electromagnetism. So how in the world do we do this? Well, we said before that we include the etheric terms due to the density of the ether in space. And when we go ahead and do what's called an actual analysis on this, all of these things come out of it. But the one thing that we should realize is that gravity is changing the density of space itself, where there's some space compartments that contain matter. But this is exactly what Einstein talked about when he talked about his theory of general relativity, that gravity changes the density of space itself. Now, this is very much of a classical theory of electromagnetism, and there is a quantum theory of electromagnetism, but to encompass everything here, including the particles, this theory is called string theory, because the subquarks from matter are actually closed vibrating strings. There are 10 strings that vibrate for matter and 5 strings that vibrate for dark matter, and they happen to be in 2 different subspaces of 10 real dimensions each. And the thing that they resonate with is it captures energy within the strings to create these particles, and so it goes. So this is the correct statement here. There's only one force, etheric electromagnetism. Now let's just take a look at what Maxwell did. He took a look at all of these different experiments that were done over the millennia. Now, each of these people, are real people: Coulomb, Gauss, Faraday, Biot, Savart, Ampere, and so forth. They carried out experiments, and they ended up with a disjointed discussion of what is electromagnetism. So Maxwell looked at all of this, and he said, okay, I can put it all into one theory, which is the theory of electromagnetism. For example, when you have an electron that moves, it creates a magnetic field. And we are familiar with the magnetic field because typically when you're in elementary school, you take a bar magnet and you get a piece of white paper and sprinkle iron filings on the paper, and you end up with a picture like we have here. Now you see what look like lines that the iron filings are following, and Faraday called this a field. So we have the lines, for example, starting at the North Pole and going to the South Pole, and then going from the South Pole back to the North Pole, however you want to talk about it. But in fact, this experiment's all true. It's been demonstrated many times, but the problem is that the iron itself contains electrons. And the electrons, when they're spinning, create their own magnetic field. So you have all these little magnets there. And as we said, the magnets like to line up. The North Pole likes to be attracted to the South Pole, and the North Pole will reject another North Pole. and South Pole will reject another South Pole. And so we came up with a little YouTube video that we put on our channel where we took a bar magnet and we put it onto a screen of a cathode ray tube, an old TV that had phosphors in it. So the phosphors are not magnetic at all. And when you do this, what you'll see is that the magnetic field is then evident on the phosphors. It starts at the North Pole, goes around to the middle of the magnet, goes into the magnet at that point, comes out of the middle of the magnet, goes down to the South Pole. Very different than the picture you see here. And so this is just an example here of something as basic as how a magnet works. You get fooled by a simple experiment here into thinking you understand it when in fact you don't. Landau and Lifshitz, who are two great Russian physicists, described what's really going on here. So here's a picture of Maxwell. And Maxwell had a compatriot, guy named Heaviside, who was not nearly the same caliber mathematician as Maxwell, but he was able to put things into forms that were much easier for people to use. So what's shown here are really the Heaviside equations modified from Maxwell for electric fields, which are the E, and magnetic fields, which are B. And the only other thing you'll see there is a J, which is a current density. Now, one of the things that's been discovered is there's no source of magnetic monopoles, but there are sources for electric monopoles. They're called electrons or protons, either one. So that's why these equations look, they should be totally symmetrical, and they're not, simply because no one has discovered these other things. We could put them in to make it look completely symmetrical. Now, you'll also see in this two little symbols. There's an epsilon sub-zero showing up here and a mu sub-zero showing up here. So this epsilon sub-zero is the electric permittivity and mu sub-zero is the magnetic susceptibility. And these relate to the strength of the electric and magnetic fields. And they're intrinsic parameters here. So those get measured, actually, they can be measured in a lab, and there's nothing sophisticated about it. But the point is that they're what they're called DC measurements. That there's no motion, there's no anything occurring like with AC, where we would look at something oscillating in time. So keeping that in mind, we're going to end up with something in a second, which you'll see. The key thing that Maxwell did when he looked at Faraday's works was he realized that Faraday actually was trying to express what's called an integral form of electromagnetism, not a differential form. So this is a differential form. There's a separate form, which is an integral form. And it's really the differential form that's the one that's widely used today. The key thing to credit Maxwell with is he realized that adding this term that Faraday had come up with, where we have a magnetic field being generated by a moving electric current, he realized that it was possible for electromagnetic waves to propagate through space. And Maxwell thought, well, the obvious thing these waves would be light waves. And this is, in fact, how light actually does propagate through space. And the one thing he missed, unfortunately, is that if you're an observer and you see one of these light waves coming at you, say, for example, think of it as a horn on a train, then when the train is coming at you, the wavefront is compressed. And when it's going away from you, the form is stretched out. And the problem is that with light, that's not the case. Light is always the same speed, no matter what the velocity is. And if you'd realized this, you would have achieved what's called special relativity. That is what Einstein did in 1905. It's a consequence of all this. And this is a picture here trying to show time going one way and a representation of space here in a so-called light cone, so that elements in time that are separated here are different than elements that are separate here in space. So that takes us up to Nikola Tesla. And Tesla, as we see here, was the person, not Marconi, who invented the first AM radio. It was Tesla, not Edison, who devised the system of electric power distribution that is used around the world. So we have generators that convert typically mechanical motion into electrical energy. And then we have motors, which are in things like the windows of your car, or your windshield wipers in your car, or your vacuum cleaner. So the motors take the electricity and convert it into mechanical motion. So Tesla invented all of this stuff, but much more. He invented a bladeless steam turbine. Think about that for a second. No blades and you have a turbine. And he invented a radio-guided torpedo. And the data that he used from the equations of Maxwell were typically, when Maxwell was doing all this stuff, they were at constant voltages and currents, or very slowly varying voltages and currents. And what Tesla did in the 1890s was he was able to generate currents and voltages that oscillated at hundreds of thousands or millions of times per second. And this led him to observe waves that were not simply transverse waves like Maxwell had permitted and claimed would be coming with electromagnetism, but they were also longitudinal, or what are called scalar waves. And the way to think about these things is that the transverse waves propagate there's a direction that the wave is propagating in, and perpendicular to it, that's why it's called transverse, is an electric and a magnetic field, and they simply rotate around each other in the direction of propagation. But the transverse, the longitudinal or scalar waves are come about. Think of having a rope attached to a fence post, and you snap the rope, so a wave goes down the rope and hits the post at the other end and can bounce back at you. So a very different sort of wave. But the power of this is that these, if we went ahead and looked at current X-ray for medicine, they use transverse electromagnetic rays, and they can't penetrate bone. But these longitudinal electromagnetic X-rays can go through bone. They can go through a lot of things, and that's why they can be weaponized, which is not necessarily a good thing. Tesla also was credited with trying out electric cars. He had an electric car in 1918, then he had another one in 1921, but there was no gasoline in the cars, and they weren't charging. They simply ran, period. No batteries, no oil, no gas, no electricity. And so it goes. And of course, he was mocked for doing this. But you know, it's one of these roads that was never taken. So let's go back to what my involvement was that Maxwell was credited with developing these equations of electromagnetism really over a 10-year period, but he really published them in the 1861, 1862 timeframe. And the key experiments here are really due to Faraday, but the others are, of course, critical. So what people miss here is that there was a German, Hermann Grassmann, shown here, who in 1847 published a book which had all of Maxwell's equations in it. 1847, not 1861. The problem with this was he did it by inventing this exterior calculus, or what are called exterior derivatives, and no one could understand what in the world he was doing. He was simply too far ahead of his time. So let's try and sketch out what he was doing. If we started with a smooth function of x, y, and z multivariate function, then we took its exterior derivative. This is actually what's called the gradient of the function. So in each direction, in the x direction, in the y direction, and the z direction, we look at the rate of change, the gradient of that function in those directions. And by doing that, we went from something that's a scalar, that it has no direction, to something that's now a vector, because it goes in all these different directions, one for each variable. Now, if we take the exterior derivative of the exterior derivative, or equivalently the gradient of the gradient, then we get a bilinear gradient. And if we repeat this, we get a trilinear and a quadrilinear gradient. If we do this 4 times, we get all the equations for electromagnetism, except with this little kicker to it that I just touched on. We need to keep in mind that the speed of light squared times the permittivity, electrical permittivity times the magnetic susceptibility equals 1. Now, this is totally bizarre, and many people have racked their brains over this. So I simply asked Ron Cowan, who had incarnated earlier as Emmy Noether, Emmy, why is this the case? And she dismissed it and said, oh, there's simply a trivial combinatoric argument here that you can go through and you'll see why it's true. So really, we're still not getting to the basis for the equations of electromagnetism, because it's got this funny little constraint in it that no one can explain. And to Emmy Noether, it's totally obvious. And why would you ever be interested in this? So I have no answer to that, but I flagged it as something to keep in mind. And Ron noticed that. I talked about a gradient before. So for example, here we've got a function of multiple variables, and you can see it has ups and downs and highs and lows. And so if we look at the rate of change, as it goes up very rapidly, there's a very high gradient. When it's very flat, there's a gradient is very low. And as we move around in the x and y directions, you can see that we get different gradients. And then if we compute the gradients of the gradients, we end up with even more. So this is what Grassmann observed. And to put it into simple forms, what Grassmann observed was that he took a scalar function, which physicists call a gauge function. And it's a scalar, so it's got a 0 form. It has no dimensions to it. No, it's not a vector, it's a scalar. And the exterior derivative of that is a vector. The vector turns out to be a potential function. And when we take the exterior derivative of that, we get a field, and this is the electric and magnetic fields that we come up with. Then when we take the exterior derivative of that, we end up with a current density, and then which is a vector. When we take the exterior derivative of that, we end up with a source function that creates the currents and the densities that we're talking about here. And that is in fact a scalar, okay? We went from 0 to 4. We only have 4 dimensions here, x, y, z, and time. So what happens here, the next thing that happens is we look at the ether following what Arnold Sommerfeld did as a perfect, and perfect here means frictionless, incompressible, meaning if we squeeze the fluid, the ether, it doesn't compress. So it's a perfect incompressible fluid. Then we get the full equations of electromagnetism, which are bolted onto this and are very complex. In fact, they would really be amenable to numerical approximations. You probably can't come up with any very simple things. I said repeatedly that these are complex. And so just as an aside, what we mean by complex here is that they were dealing with complex numbers. Complex numbers have two pieces to them, a real part, and here we're calling that real part A, and an imaginary part, which you call B, and the complex number Z is shown here as A plus B times the square root of -1, which is I. And so we need this. This is apparently intrinsic to what's going on here for describing the underlying electromagnetism, which is what Ron observed. So if we go back to this, I just touched on this early. There's a magnetic susceptibility, and we see down here at the bottom that the magnetic field B is related to the H field by the permeability mu here. And if we go to the electric field, there's a displacement field D, which is related to the electric field by the permittivity epsilon here. And in free space, those simply take on certain numbers. And we have to remember that when we multiply, as we saw, the permittivity times the susceptibility times the speed of light squared, we get 1. Not at all obvious. So my work in this was, again, my thesis advisor asked me to go investigate Grassmann's work. I went ahead and wrote all this up and just documenting it here. That matched what Grassmann had done. And then in 2005, I went through Sommerfeld's work on the equations of electromagnetism, including the notion of an ether, and that led to these equations here. And the obvious thing that you do here is the ether is probably very thin. It's probably very close to 0. So this suggests doing what's called the perturbation expansion, where we do kind of a power series. We have a 0th power of the ether. We have a first power of the ether density, a second power of the ether density. And because this is a lot less than 1, these other terms are really negligible. So in doing this, the 0th order terms in this analysis are really Maxwell's equations in free space. But the first and second order terms actually result in the strong force, which we said was that the positive charges attract one another at close enough distances in the nucleus, and also the weak force, which generates these isotopes inside the neutrons turning into a proton and an electron and a neutrino. And then gravity is the result of the change in density of the ether, which is really what Einstein showed in general relativity, but in a completely geometric manner. And Einstein didn't include electromagnetism. So that's our one nice, well buttoned up area of electromagnetism that took several hundred years to come up with this. And here we are today, and we're still not done because we can't explain some very simple, obvious things. So now we're going to turn to the real crisis, which is that 95% of the universe is what's called dark. We have dark matter, and that was first really accounted for when telescopes were good enough to resolve smudges of light to be other galaxies. And there were numerous of these spiral galaxies. And so observations started in the 1920s, but culminating in the early 1930s, Fritz Zwicky, who was at Caltech, went ahead and did an analysis where he said, okay, let's suppose that the galaxy contains stars and that they're the average mass of our sun. They attract each other by gravity. Then what happens, and what he showed was that these galaxies would fly apart. They're not stable whatsoever. So there's some additional unseen, what is called dark matter. You can't see it with telescopes, which generates the sufficient gravitational attraction to hold the spinning spiral of stars together. And it turns out that This was confirmed with lots of other observations, culminating in a really major work in 1970 by Vera Rubin. And currently, dark matter is estimated to be 27% of the universe, and matter is estimated to be 5% of the universe. This takes us to dark energy. And here, Edwin Hubble, using the telescopes at Caltech in Pasadena, Mount Wilson Observatory, that is suggested that all of these galaxies are moving away from one another. And he attributed this to an unseen energy, which he simply called dark energy, which is 68% of the mass and energy in the universe. So the dark energy actually appears to involve having a slight expansion of all of the space compartments in space themselves, which is mind-boggling, to put it mildly. It isn't that they're moving away, it's that space itself is expanding. So yes, you get further away because the space in between you is now bigger. So this is really what Ron came up with. This is an amazing accomplishment, but just to motivate it, let's say that we've got 5% of the universe in 3 spatial dimensions. So if 5% is in 3 spatial dimensions, then to get 100% of the universe, we take 3 and divide it by 0.05, and we see we need 60 dimensions. There's other dimensions there besides the 3 that we deal with that contain all this dark energy and dark matter. And what Ron showed was there's actually 24 real spatial dimensions. There's also 2 time dimensions. And so we have 26 real dimensions, 24 spatial, 2 time, and we'll come back to these. It might be helpful, though, to pair these things up, especially because we touched on the notion of complex numbers, and just thinking of these dimensions, we have 3 dimensions, say X, Y, and Z. The space-time dimensions for matter include time multiplied by I, the square root of -1 times c. C is the speed of light, so the speed of light times time reduces us to meters per second, meters, period. And X, Y, and Z are measured in meters. But now we rotate it by 90 degrees. If you look back at our little complex chart there, if we multiply by square root of -1, we rotate something from being totally real to totally imaginary, or it's a 90-degree rotation. So we have these 4 dimensions here for space and time, and so we rotate those by 90 degrees by multiplying by square root of -1, and that gives us the dark matter dimension. So if we follow this through, we really have just 4 space-time dimensions for matter, 4 space-time dimensions for dark matter, or we have 8 dimensions total, but we really have 4 complex dimensions. The real part is due to matter, and the imaginary part is due to dark matter, just to simplify things a little bit. And then we have compactified dimensions, and this is where Ron excelled. There were 18 compactified dimensions, but 6 of them go with matter, 6 of them go with dark matter, and 6 of them synchronize between these 2 different subspaces of matter and dark matter. So dark matter has a 10-dimensional subspace, matter has a 10-dimensional subspace, and we have a 6-dimensional synchronizing subspace here. The thing that he observed was that there's 3 holes here, and the 3 holes result in being connected to the 3 holes in the synchronizing space, which has 8 holes. The dark matter has 4 holes, so 4 of those holes connect to the 4 of the 8 holes in the synchronizing space, and that leaves us with 1 hole left over. We've connected 7 out of the 8, so the final hole connects between 2 of these 6 dimensions in the synchronizing space, and the end result is we have really 18 dimensions here, but with the 8 holes being all interconnected. there's really only 10 dimensions. And so this is important because it checks out that in the Kabbalah, there's 10 nodes in the tree of life, 10 dimensions there that the mystics observed. And that's exactly what's going on here. And so it goes. So this is a huge accomplishment that Ron came up with. The other thing to keep in mind here is there's these holes and what's going on here with them. But let's go back for a second to what is a compactified dimension. So in 1926, a German physicist, theoretical physicist Oscar Klein, looked at a 5-dimensional theory of electromagnetism and gravity by Kaluza, who had extended Einstein's work. And everyone wondered, where's the 5th dimension? And so Klein suggested that this extra 5th dimension, it could take the form of a circle, something that was rolled up that would be running down one of the dimensions. It's shown here as there's a 2-dimensional space that's wraps around one dimension. But the measure of this thing is it's on the order of the size of a compartment of space, very, very small. And so we don't have any way of observing this, but we think it's there. And this was followed through by 2 mathematicians, Eugene Calabi, who proposed these sorts of manifolds that would be compactified, and Xington Yao, who actually showed that they existed. And in particular, ended up showing that there's probably a little under 10,000 of these Calabi-Yau manifolds. So there's movies on YouTube. Here we've got a 2-dimensional representation of a 6-dimensional Calabi-Yau manifold. Here's a different one down here, and there's many, many more. And so these things morph and evolve and twist and turn in every which way. And it's an amazing, very beautiful thing to go watch any of these YouTube videos. But the properties of these are highly technical. They have basically the key thing about this is that they're basically flat. That if you're at any given point on one of these manifolds, it looks flat. But as you start to get away from that point, you start to see it curving. So that's really the crux of it. There isn't any there's other spaces out there that have these things, but it is what it is. The thing that Ron touched on with these holes is important. It shows up in the Kabbalah, but it also shows up in modern physics. So in the Standard Model, it was developed around 1975, which is shown as a picture here. There's a bunch of primary particles. So the electron has 2 other resonance states. The electron neutrino, which is shown here, has 2 other resonance states, or there's a total of 3 states. Well, that's a tip-off that matter has 3 holes in it in the compactified Calabi-Yau manifold. So there's really only 1 electron, but it resonates because of these 3 holes that are there in this manifold, and these other things here. Similarly, all of these resonances here that are occurring for these photons that are there, these bosons, including the Higgs boson, which is shown right in the center, are really all representations of 1 single photon that's been excited into different spaces. So this picture for matter can be significantly simplified. There's a similar figure for dark matter, but it doesn't have any charge to it. So things like electrons and so forth are absent. There's only the subquarks for dark matter, which have 4 resonances, because we saw there are 4 holes there. And then we have to include space, and the space compartments themselves end up interacting with these two different things, and so it goes. So that's what you can expect to see happen over the next 5 to 10 years. Now, we touched on time and having two time dimensions. We have dark matter, and they each have a different time dimension. Now, what we've actually seen in this, and we've seen this before, is that there's, in physics, there's a interpretation of physics in quantum mechanics where at every instant that there's a change in state, the universe splits into a separate universe. We have a separate timeline, or as it's called, a many worlds evolution of the universe. So every instant in time creates every transition that occurs, say of an electron hopping from one level to another in an atom, that by itself creates another timeline. And there's incredible numbers of these transitions occurring, billions upon billions per second. There's many, many possible timelines, many possible worlds. And the reality is that the path that we're on is in some sense unique to each of us, but we sense this mainstream path that we all run on, and that controls the things that branch off from this are dead ends, and they apparently simply die out and are not of interest. But this remains to be explored. So if that's what happens with the time dimension here for matter, then with this many worlds interpretation here of this, this also leads us into this so-called pilot wave theory that David Bohm came up with, which Ron confirmed, which is that there's these information blocks everywhere that form these pilot waves that are scanning everything in the universe and reacting to it. And so the things that branch off in some sense will die out because they're really not following these algorithms that are caught here inside all these space compartments. The dark matter time is what would be called in the Hindu Vedic records, the Akashic record. So the idea here is that time captures all of the events tied to a particular soul. A soul lives over here in this dark matter dimension. Remember that here we have matter, and matters achieve consciousness here. So dark matter can also achieve consciousness, as can energy. Energy can achieve sentience or consciousness. So we can have energy beings, mass beings, dark matter beings, matter beings. The dark matter entities we would call souls or spirits. And these souls have a particular timeline associated with them from the beginning of the universe to the end of the universe. And this is the Akashic record that allows traveling up and down in time from the past to the future. So every time you incarnate, this veil of ignorance kicks in. The Akashic timeline is not at all visible, but the soul can still see this. And this is what happens when people go through this hypnotic regression to past lives, is they access this Akashic records. And the key example that comes up that the CIA discovered was that a number of individuals were hypnotically regressed back to lives that were in the Civil War, and they remembered the South winning the Civil War. And so this is an example of a timeline that was apparently quite close to our current timeline, but our timeline, the South lost the Civil War. So you can start to see the rabbit hole that you go down in dealing with these things. The Akashic record is really an incredible film. So it registers everything in your life, all of your experiences, all of the lights, the sounds, anything you can think of. It's the most incredible 3D movie you could come up with. And the thing to keep in mind here is that this is a very different sort of time than the time that we're living through. So we come back to Ron Cowan, And Ron was this Canadian Buddhist monk. He taught in high school physics in Toronto, and he published 2 books. I've shown them here. They're both available on Amazon. The Path of Love, The Future of Buddhism as a Science, and How Mindfulness Meditation Works, a Modern Buddhist View. And we worked together from, say, 2016 to his death in 2019. One of the things that he did here in his book on the future of Buddhism as a science was he actually went in and observed the chakras and observed that they appear to be dark matter, that each of us have in these 7 major chakras, dark matter, and then we have resonances that occur around this that lead to other chakras that are totally energetic, not dealing with dark matter. But we didn't explore this because there was too many things to go observe, and as it was, we missed a lot of things anyway, but we gave it our best. And the chakras we see here, just this is the standard picture you'll see, and perhaps these chakras have a single vortex, a single linkage here. The top chakra and the bottom chakra apparently have 1 vortex, and the other 5 have 2 vortices going forward and backwards. So we could say we have 12 chakras, if you want to think of these vortices that way. And apparently these chakras provide a material anchor for the energy of the soul. The one thing that we skipped over, we never talked about, was I asked Ron to take a look at the curvature in this, particularly in these compactified spaces, and that's characterized by this Hodge diamond, which is a description of the curvature in each of the different directions, or if you will, the gradient, how the curvature is changing in each of the different directions. And while it's been recorded, we don't know what to do with it right now. It's something that's known, but we simply ran out of time to do anything with it. Another thing that Ron explained was the duality of matter being both a particle and a wave. So the key experiment that was always cited was the ability to take an electron beam and shoot it through a slit, and on the other side of the slit you'd have a foil and you'd see a line of electrons. But if you put 2 slits there that were close to one another and the electrons were shot at the 2 slits, then you ended up with a diffraction pattern. And this generated interference constructively and destructively. So you had a wave pattern occurring there, so that what was you thought was an electron actually behaved as a wave. Now, Louis de Broglie in 1924 postulated that there was that everything was dual, that matter was a wave and waves were matter. And that was his doctoral dissertation. He got the Nobel Prize for this. Now, he postulated for this double slit experiment, there was a pilot wave that sensed whether there were 2 slits or 1 slit and behaved accordingly. And David Bohm picked up this idea in the 1960s and developed a pilot theory of quantum mechanics that's completely consistent with all of the existing theory of quantum mechanics and could explain the double slit experiment. And Ron did this under deep meditation. He saw that the electron was in fact coated with these blocks of information. They were constantly scanning. Once they detected that there were 2 slits, the electron became a wave and acted accordingly. And so here's a beautiful picture Ron made of an electron with 10 of these closed vibrating strings. They resonate and capture energy, which is shown here. Ron was able to just freeze this to be able to go do these sorts of drawings. But the energy, think of it as kind of a jelly, electromagnetic energy of this thing vibrating like crazy. And there's a hole through it. So it's really a donut or a torus when you look down at the very, very small hole. But this is what makes up an electron. And then the electron is coated with these blocks of information that are constantly scanning the world around us. And because he did this for the electron, there's nothing to suggest that electron is unique in doing this. So we have to think that protons and neutrons and any other things, in particular photons, or what are called bosons, are coded with these information blocks, and it allows them to cover everything. So one of the things I forgot to mention here, we go back to this here, is that we have the matter behaving in this 10-dimensional space here, the dark matter in this 10-dimensional space, but the bosons run in all 26 dimensions. These photons that make up electromagnetic fields run in all 26 dimensions. And that is what makes them very different than everything else, obviously. So that is it for tonight. Next week, we're going to take a look at trying to close this out, but for now, we're done. Any comments, Bruce?
Wow.
Ron is due credit. He did great work.
Yeah, he was very excited. How he described it to me is that he was observing an electron traveling through space, and it would suddenly disappear and then reappear further along the way that it was following. And he could see that it expanded to the rest of the universe and came back again. And that information was recorded in the electron. And he was very excited and inspired by that observation.
Yeah, it's a fundamental point of confusion in modern physics as to how to explain this. Right now, there really isn't any good explanation, but Ron has the first one.
Right. Well, to me, what it means.
This is based on observation.
Yeah.
And observation is worth everything in physics. Just having a theory is worth nothing.
Right. To me, it's kind of like, it's like the universe is in union with itself.
Yeah. And it's amazing he was able to, he saw things that Leadbeater and Besant never saw. They never saw dark matter.
Right.
And he was able to stop these things. So they're vibrating like crazy, hundreds of millions of times per second. He's able to stop them.
Yeah. See, what you need is a team of meditators who can do all these things. And but the big thing is that science has to recognize that the mind is a legitimate area of study.
Right.
Big problem.
It's part of the universe, or a reflection of the universe. We can't experience or imagine the universe without the mind, but it's the instrument in question is also, the same thing that's being examined.
The other thing that we missed was seeing this expansion, seeing the scanning take place for this electron, for example. What is really going? Is some sort of radiation, or what is it that is doing the scanning, expanding? We just don't have any handle on it yet.
Well, you need another run.
Yeah. Yeah, and there's undoubtedly many other things we missed, but at least it's a good start, I think, toward explaining what's going on. There's a lot of evidence that Tesla, once he discovered this, I'll just say, longitudinal waves out there, he went to Colorado Springs and he set up a lab there, and there's notebooks available, which I read. They're available for sale on Amazon. And it was clear that he was building like a flying machine. He would be flying in the night at Colorado Springs because he didn't want anyone to see him during the day. And that's just who he was. He was combination experimentalist and theoretician. And he went and he took light bulbs, and he said, well, we want to have light everywhere, so we can either transmit it through the ground or through the air. So he actually went out and planted light bulbs in the ground, and he lit up light bulbs going out, a quarter of a mile in all directions. Now, how in the world did he do that? There weren't any wires there. And then he lit them up by broadcasting through the air. So they were energized that way. So you get people like that, you scratch your head and wonder what else did they know?
Right. Well, this is back to one of my main points about the mind or consciousness is that there's many levels of insight and awareness. Like these are natural parts of everyone's mind. And Ron was good at tapping into them, but every mind has that reality.
Right.
And,
Yeah.
I mean, the other thing is that I've encountered some very enlightened teachers who naturally have this level of understanding.
Yeah, the thing that comes back to it is that it really appears that it's the mathematics or the meta-mathematics that appears to be more fundamental for setting up the ground rules than the physics is. And that's a very different point of view.
Right.
Physicists would object to that, of course.
What I liked about this talk was that it showed that the mathematics is inherent. It's not being applied to the reality of the situation. It's the structure is built in to what's there. So it's as if the universe is generated along these mathematical principles from the inside out, on the most fundamental level. It is mathematically constructed.
Yeah.
I don't know if I'm saying that right, but
no, that's what this physicist Stephen Wolfram has been doing all this work on, and concluded that you really do have these many timelines, and you really do have the algorithms being the essential part to it all, to generate what we would call physics today. Again, he's got a long ways to go, and he needs a lot of experiments to back up what he's been trying to show theoretically. So we'll see, but there's too many things happening right now. To me, it's very much like physics was in the 1920s, where there was a huge amount of activity by very smart people all over the world, but the concentration happened to be in Germany, and to a lesser extent France and England, and the U.S. was just along for the ride. There were people that visited Germany, like what's his face, Linus Pauling, or Robert Oppenheimer, were both in grad school then, and they went to Germany and worked firsthand with these people. But that was kind of it for the United States. And now you have China with all of these schools cranking out, very, very capable people. So we'll see what happens. There's just too many things breaking right now. I think there'll be a lot of very interesting advances that will come out, or hopefully will come out. Problem is the black ops guys want to go suppress all this stuff, but that's another part of life. So Anyway, we'll see you next week. That's what we're
Okay.
just set the foundations, and next week you'll see is a very different thing what we're doing. So have a good and
Okay.
onward and upward.
Stay warm.
Yep, stay warm. Okay, bye-bye.
Bye.